Good morning to all of you.
Good morning, sir.
Good morning. So is my screen visible?
Yes, sir.
Okay. So are there any questions, doubts? Yeah. Anybody? Any question? Any doubt? Okay. So then let me start. Yeah. So I was not discussing dynamics. So let me continue with that. Okay. It is not writing. So let me close and open. Is the screen visible?
Yes, sir.
Okay. So yeah, I'm continuing with dynamics. So yeah, last class I was trying to derive the equation of motion. So we used Hamilton's principle. So Hamilton's principle statement is that integral from t1 to t2 delta t minus delta v plus delta w and c dt equal to 0. So this is the Hamilton's principle statement, where delta t is the first variation of kinetic energy, delta v is the first variation of potential energy, and delta w and c is the virtual work of non-conservative forces. So for the the truss element, we wrote the final expression as minus t1 to t2 and delta of d transpose, and then we had this me into de double dot plus ke into de minus f external for the element minus f internal for the element dt equal to 0. So this is where I left in the last class. So we said that no, this integral has to be 0. Now for this integral to be 0, the integrand has to be 0, and integrand is product of two things, delta d transpose and the other terms. So since no, this should be 0 for arbitrary delta d, so therefore the other term has to be a null vector. So since delta de is arbitrary, so no, then the second term of the integrand has to be 0, and that gives you the equation of motion me into de double dot plus ke into de is equal to f external for the element plus f internal for the element. So yeah, this is the equation of motion. So we call it as element level equation of motion. And you see that this is the additional term, now the inertia term, mass matrix into acceleration vector, that's the additional term, this term, which is coming in the dynamics equation of motion. So this whole thing is referred to as element level equation of motion. Now let me show you an example. Although no, you might have done in the basic FEM course, but yeah, I'll just again revise that kind of. So let us say we have this rod which is undergoing axial vibrations. So this is the distributed load acting on the rod, and let us say we discretize this into two elements. So element 1 and element 2. The nodes are, this is node number 1, global node number 2, and this is global node number 3, and each element is of same length L, and the properties are E is the Young's modulus, rho is the density, A is the cross-sectional area of the elements, and Q is the distributed load. So this is Q. And there is a global degrees of freedom. So that is at each node, let us say this is, let me denote it by U1, which is a function of t. This is U2, which is a function of t. And this node has displacement U3, which is a function of t. So now if you want to write the equation for the whole system, so assembly comes into picture, and in the assembly, as you see here, for the system as a whole, there are 3 nodes and 3 global degrees of freedom. So the overall size of mass matrix, stiffness matrix is going to be 3 by 3, and the load vectors would be 3 by 1. So now if you look at, let me first just put the block. So this is the degrees of, the acceleration vector u1 double dot, u2 double dot, and u3 double dot, plus we have stiffness, and then u1, u2, u3, 3 degrees of freedom, and then is equal to right hand side you have the 2 load vectors. So this is the structure. So in the mass matrix we have derived for this truss element. So let me take, because we are taking both the elements are of same length, and the cross sectional area, density, Young's modulus are constant and same in both the elements. So then here I can take rho al by 6 common. So now the first element is defined between global nodes 1 and 2. So its first row and column will go to the first row and column, second row and column will go to the second row and column, because it is consisting of first 2 global nodes. So the first element mass matrix 2 1 here, 1 and 2 will go like this, and wherever nothing is there, that's 0. And second element is defined between nodes 2 and 3. So its contribution will go to row number 2, 3, column 2 and 3. So it will be, element number 2 will be going into the second row, second column, second row, third column, and third row, second column, and second row, third row, third column. So this is the mass matrix, assembled mass matrix. And similarly the stiffness matrix, so let us say this EA by L is common in the stiffness matrix, and then the first element will go into the first 2 rows and columns. So 1, minus 1, minus 1 and 1, then this is 0, this is 0, and here the addition second element go into the second and third rows and columns. So plus 1, minus 1 and 1. So this is how the stiffness will be there. and then the load vector due to distributed force Q, which is along the axial direction. So if I take QL by 2 common, so then the first element will go into the first row and second row. So 1 and 1 here. Then the second element contribution will go to the second row and third row. So plus 1 here and 1 here. And then the internal forces. So first element it is Q1 1 and then Q2 1. That's the first element. And then the second element minus Q1 2 and Q2 2. So these two are from the first element and these two are from the second element. So this is how the overall the assembled equation of motion is going to be. Now you see that when I have written this internal load vector, so first element we are assuming that the internal forces are Q11, Q21, and second element the internal forces are Q12 and Q22. So these are added into this internal load vector. Now if you look at let's look at the boundary condition. So what is the final equation which we integrate or solve for the response? So the final equation is, if I look at the boundary conditions, so the boundary conditions number 1, as for this, see this assembled system, what I have written here is you can have any boundary condition. So this is independent of boundary condition, but next what we are going to develop is depends on the boundary conditions. So now the first node is actually fixed. So u1t at all time instances is 0. So you will have u1t equal to 0, and since u1 at all time instances is 0, u1 dot would be 0, u1 double dot will be 0. So that's one set of boundary conditions. Second is, if you look at node 3 is a free node. Here there is no external load, concentrated load applied. So that is at node 3 we will have this Q22 at all time instances will be equal to 0. And the third condition is, if you look at node 2, so we will have this Q2 1 minus Q12 equal to 0. This is coming from the basically the equation of motion for node 2. So this side is the force Q21. This is opposite to what is shown in the element, because this I am showing at the node 2, and this is Q12. And since the node is of node we are taking as a of mass 0, so we will get Q12 minus Q21 is equal to 0. So these are the boundary conditions. So if we impose these boundary conditions and then write the equations which are in terms of the unknown displacement. So in this case u2 and u3 are unknown displacement. So we just take the second and third equation, and then we solve for u2 u3 as a function of time, and then of course from first equation we can solve for q11. So final equation of motion, if we look at the equation of motion which we use for solving deriving eigenvalue problem and solving or finding out the dynamic response, so that's the final equation I am referring. So final equation of motion after imposing boundary conditions. So the final equation of motion, that means because u1 is known, so we take the second and third equation in terms of unknowns u2 and u3. So the equation would be rho al by 6, and then here we have 4 1 1 and 2 into u2 double dot u3 double dot, plus we have this ea by l 2 minus 1 and 1 and then we have u1 u2, and is equal to right hand side will be just left with ql and ql by 2. So this is the final equation of motion, and usually this be
Sir,
right in yeah. Yes.
we have U2, U3, like
Yeah. Yeah, yeah,
not EU.
yeah, yeah, yeah. Sorry. Yeah, yeah. Thanks for correcting this. So this is U2 and U3. So yeah, this is the final equation of motion. So now symbolically we write this equation as the mass matrix M into D double dot plus stiffness matrix K into D is equal to F. Where M in this case is this, K is this, F is this, D is this, and D double dot is of course the acceleration vector. So now here usually we call M as the what we have got as the global mass matrix, and K is the global stiffness matrix, and F is the global load vector. And global D is a function of time, so that is global displacement vector, global nodal displacement vector. Nodal displacement vector. So yeah, this is what. So now that's the final form of equation of motion. Now this equation you can solve as a eigenvalue problem. So f equal to 0, and d you can take as capital D into e to the power I omega n t, and then derive an eigenvalue problem for doing the modal analysis. Or you can, for a given f as a function of time, you can integrate this and get the dynamic response, or take f equal to 0 and some initial condition and solve this, to you will get the free vibration response. So those are the various analysis you can do using this equation what we have got over here. So you will see that the difference is that we have this additional term, the inertia term, mass matrix into acceleration vector, that is the the additional term. So now let's look at for few more elements how to do. So the dynamic equation of motion is going to be of the same form. So let's also look at this mass matrix for few more elements, the basic elements, basic finite elements. So next I am going to talk about the mass matrix for Euler-Bernoulli beam element.
Sir, one doubt.
Yeah,
Sir, the equation we have got, it also has the acceleration term.
yeah,
So how will we like solve this equation, sir?
yeah. So the
Like,
solution, because this is a u2 double dot and u3 double dot are second derivatives of u2 and u3. So you can there are different way. If you want to solve an eigenvalue problem, then you will write the vector d as capital D into e to the power I omega t. So by
okay,
differentiating that, you will get d double dot. So that is how you do it.
okay, sir. So basically, how we do in vibration, we have to follow the similar method.
Yeah, yeah, same thing. Yes, yes. So the role of finite element is just to give you this equation. Rest of the things
Okay,
what you do in vibrations, all those for multi-degree of freedom system, whatever you do, all of those are applicable for further solution of this equation.
okay, sir.
Yeah. So now let me look at this Euler-Bernoulli beam element. So now in the Euler-Bernoulli beam element, let us say, this is the I'm just talking about, starting with directly single element. So these are the local node numbers 1 and 2. The local coordinate system is capital X and capital Y, and then in the deformed configuration, say this element deforms like this. So initially we have a normal, like this normal, and then this takes if I this takes a shape like this. This is the final normal. So if you look at this distance, displacement along x direction, that is y into del v by del x. So now for this element, if you look at the displacement field, so here small u is the displacement along x direction, which is a function of x, y, and t. So that can be written as, for the small deformation, minus y into del v by del x. And another displacement is v, which is assumed to be a function of only x and t. Then because in the kinetic for the mass matrix we need the velocities. So velocities are u dot. So u dot would be by differentiating this equation, we get u dot is equal to minus y into del v by del x dot. Dot denotes the derivative with respect to time. So you should keep in mind that everywhere dot denotes derivative with respect to time. Single dot means first derivative and double dot means second derivative. The other component of velocity is simply v dot along the y direction. So now if I want to write the kinetic energy, you can also derive this element level equation of motion starting from the differential equation of motion, then writing its better residual statement and weak form. So from there also it's possible. So I am following the energy waste approach. So kinetic energy, then T for this is going to be half integration 0 to L integration over the cross sectional area rho, and this formula is same. There are two velocity components, so u dot square plus v dot square dA dx. So this is the kinetic energy. Now if you substitute the velocity component, so half integration 0 to L integration over the cross sectional area and rho, and then the first term is y square into del v dot by del x whole square plus v dot square dA dx. So now this we can write t equal to, we do the integration through the cross section. So we get integral 0 to a. The first term is rho into y square dA. Y square dA is actually izz. The area moment of inertia about z axis. So this can be written as rho into izz, the first term, into del v dot by del x whole square. The second term integral rho dA will be rho into a. So rho into a into v dot square dx. So this is what it would be. Now usually this is known as the rotary inertia. No, rho into izz is rotary inertia, and for thin beams this is actually negligible compared to rho a into v dot square. So for thin beams for which the Euler-Bernoulli beam theory is applicable is actually negligible compared to rho a into v dot square. So that means the kinetic energy can be approximated as half of integral 0 to L rho a v dot square dx. And so finally we can write that T as half integration 0 to L rho a, and for substituting v in terms of matrix interpolation matrix and vector of elemental degrees of freedom, we write it as v dot transpose into v dot dx. So now if you look at the interpolation, so I am directly writing this assuming that you would have done Euler-Bernoulli beam element. So that V of xt would be in terms of four shape functions. So that is H1 is Hermite interpolation functions, H1 H3 H1 H2 H3 H4 into vector of elemental degrees of freedom. So that is V1 is a function of time, theta 1 is a function of time, V2 is a function of time, and theta 2 is a function of time. V1 is the displacement at first node, theta 1 is the dV by dx at first node, V2 is the displacement of second node, and the theta 2 is dV by dx at second node. So you can also write this as interpolation matrix H into dE.
Sir, while replacing V dot square, why are we taking V dot transpose 2 times?
Oh, no, I'm sorry. Yeah, this is only one.
Yes, sir.
This is V dot transpose into V dot.
Yes, sir.
So now this is H into D, and for the Hermite interpolation function, so let me also write the expressions for these. So where Hermite interpolation functions are, h1 is equal to 1 minus 3 x square upon L square plus 2x cube upon L cube, and the h2 interpolation function is x minus 2x square upon L plus x cube by L square, and h3 is 3x square upon L square minus 2x cube upon L cube. So these are the Hermite interpolation functions you can derive. H4 is minus x square by L plus x cube by L square. So these are the interpolation functions, and theta 1 t is basically dV by dx at node 1, and theta 2 t is dV by dx at node 2. So now if you can, now similarly we have V given by this expression, so we can also write the V dot will be, the H is only function of capital X, the local element coordinate system. D is a function of time, so we take its derivative. So this V dot would be H into dE dot. So now if you look at the kinetic energy, so you can write this kinetic energy T as half of integration 0 to L, and then we have rho A, and now V dot transpose would be dE dot transpose into H transpose, and then V dot. So V dot is H into dE dot dx. So now if you because this d dot is independent of x, so can be taken out of the integration sign, so we can write here t equal to half integration 0 to L, no, I want to, let me, half, and then here d dot transpose into inside the integration, inside the integration 0 to L rho A, and then we have H transpose into H into dx, and then again this d dot outside the integration sign. So this is what we call as, this has a mass matrix, what we have at the center. So this is half m into dE dot transpose into ME, element level mass matrix, into dE dot, where ME is basically this. So where element level mass matrix for Euler-Bernoulli beam element is equal to ME equal to integration 0 to L rho A H transpose into H dx. So now if you substitute H is H1, H2, H3, H4, So if you substitute that and multiply the two H transpose into H, so finally we'll get ME is equal to integration 0 to L rho A, and here you are going to get this is a 4 by 4 matrix into dx. You need to integrate each and every term. So this would be h1 square, h1 into h2, h1 into h3, h1 into h4, then h2 into h1, h2 square, h2 into h3, h2 into h4, then you will have h3 into h1, h3 into h2, h3 square, h3 into h4, then you will have h4 into h1, h4 into h2, h4 into h3, and h4 square. So this is what you will get. And now the shape functions already defined. So assuming that, let us say the rho a is constant within the element, so then we can write this as rho al by, so this, now if you perform the integration, so finally this comes out as the mass matrix. So this is the elements are 156, 22L, 54 minus 13L, and then 22L, 4L square, 13L minus 3L square. The third row is 54, 13L, 156 minus 22L square, and this is minus 13L minus 3L square minus 22L and 4L square. So this is the mass matrix for the Euler-Bernoulli beam element if rho A is constant within the element. So this is what you get as the mass matrix, and as we discussed in the last class, this is known as consistent mass matrix. This is known as consistent mass matrix, and in this case, because in the Euler-Bernoulli beam element, in the element you have basically the only the both translational as well as the rotational degree of freedom. So we had seen in the truss element where you have only the translational degrees of freedom. So sum of all the elements of mass matrix was equal to total mass. In this case, sum of all the elements of the mass matrix corresponding to translational degrees of freedom would be equal to total mass. So you will have this 156, 54, 54, and this 156. If you sum these, so 156 will give you 312, and then plus 420. So if you sum this, and this, these are the the elements of the mass matrix corresponding to translational degrees of freedom. Because now the d1 theta, we have v1 theta 1, v2 theta 2. So the first row, and out of that the first and third columns are corresponding to translational degrees of freedom, and similarly third row and the first and third columns are corresponding to translational degrees of freedom. So sum of these is what is equal to total mass, rho al. So that's the another property you will see now here, the way we discussed for the other one. Sometimes we also use what is known as lumped mass matrix. So without going through the derivation consistent with the interpolation matrix, we simply write what is known as the lumped mass matrix. So we take the total mass, the lumped mass matrix of course can be written in different ways. So lumped mass matrix, one way is that we take the total mass and distribute at node 1 and 2 corresponding to translational degree of freedom. So that is simply rho al by 2, and then only the translational degree of freedom. So that is diagonal terms essentially. So we are distributing only at the first and second node. So this could be one of the lumped mass matrix. Of course, there are other ways also to write this. So the one of the ways to write the lumped mass matrix is this.
Excuse me,
So
sir.
yeah,
So why we are doing this? Like we are distributing the mass only corresponding to the translational degree of freedom. Why not to the
yeah,
rotational, sir?
you can also do that. So this is, as I said, the one way of doing it. So you just distribute between the diagonal elements of the translational degree of freedom. You can also take the rotary inertia and distribute the other diagonal elements corresponding to theta 1 and theta 2. So that is also possible. So this is one way of writing lumped mass matrix. It's not the only way.
Okay, and so one more thing, like if we see in the consistent mass matrix, the
Yeah,
whole mass of the Euler-Bernoulli beam is the summation of the only translational. So what is the
yeah.
physics behind it, sir? Like,
Because that is corresponds to the translation. So the total mass which is kind of translating is corresponding to the translational degrees of freedom. So that is related to translation. See, and similar to what we did for the truss element.
oh, okay, sir. Thank you, sir.
Yeah.
Sir,
So now, yeah,
this we have written only for one element till now.
yeah,
And first case, we actually used Hermite interpolation function. So
yeah,
that is why we got that matrix.
yeah,
Uh, in this case, we are directly assuming that this kind of mass matrix is there and we will be using this, right?
yeah, right, right, yeah.
Okay, sir.
So there are other ways of actually obtaining the lumped mass matrix from the consistent mass matrix. So first you retain only the diagonal terms and then make sure that the total mass is sum of the two diagonal elements corresponding to translational degree of freedom is equal to total mass. So that way also you can derive the lumped mass matrix. So there are different ways. So this is one way of one of the ways to write the lumped mass matrix. Now if you look at the using the Hamilton's principle, using the same approach you can write the element level equation of motion. So element level equation of motion is going to be now the form is going to be same, me into de double dot plus ke into de is equal to f external for the element plus f internal. So this is what you get as the the element level basically the equation of motion in this form, and where me we have already defined, and ke is the stiffness matrix for the this Euler-Bernoulli beam element. So where you would have done this, so ke is basically integral 0 to L ei and d2h by rather del 2, because yeah, d2 is fine because h is only function of x. So d2h by dx square transpose into d2h by dx square dx. And for this also, for solving problems you need the mass matrix and also the stiffness matrix also. So if ei is constant throughout the element, then we can write this as ei by L cube, and then the stiffness matrix is 12 6L minus 12 6L, and then 6L 4L square minus 6L 2L square, and then minus 12 minus 6L 12 minus 6L, and then this is 6L 2L square minus 6L and 4L square. So this is if ei is constant within the element. Similarly, the F external load vector, that is equal to, if we assume that q is constant, so can be written as integral 0 to q into h transpose dx. And if q is constant within the element, then it is ql by 2, ql square by 12, ql by 2 minus ql square by 12. So this is the external load vector for this element, Euler-Bernoulli beam element. And F internal for the element is minus V1 minus M1, V2 and M2. The V is shear force and M is a bending moment. So that is at the ends of the element. You have here capital V2, M2, and this side you have V1 and M1. So this forms the basically the the element level equation of motion for the Euler-Bernoulli beam element. Now if I again take an example, so let me again let us take a beam and discretize that into basically two elements. Although you can discretize into any number of elements, but just to demonstrate, I am discretizing into two elements. So that is node number 1 here, node number 2, and node number 3. These are the global node numbers, and there is a distributed force throughout the beam. So we have this Q, this load is Q. This is element number 1, this is element number 2, and length of this element is L, length of this is also L. Both the elements are of length L. The properties, if you look at the property of the beam, E is the Young's modulus, I is the area moment of inertia about z axis. So your IZZ is I, and rho is the density, A is the cross sectional area, and Q is the distributed load. So these are the properties. Now if you discretize this into two elements, each node is having 2 degrees of freedom, so total there would be 6 degrees of freedom. So when you write the you have to first do the assembly and develop the this global equation of motion. So in the assembly you will have mass matrix which will be of size 6 by 6 because total 6 degrees of freedom, and stiffness matrix will be of size 6 by 6. So that is going to be, so if I write over here, so this is the you will have mass matrix into acceleration vector plus then you will have stiffness matrix into displacement vector. So the acceleration vector is going to be v1 double dot, theta 1 double dot, v2 double dot, theta 2 double dot, v3 double dot, and theta 3 double dot. And this side you will have the displacement size v1, theta 1, v2, theta 2, v3, and theta 3. So now if you assemble the mass matrix, so I am assuming that both the elements are of same length, and rho into A is also same for both the elements. So you can take this rho AL upon 420 as common if we are using consistent mass matrix. So now the first element is defined between global nodes 1 and 2. So it's the 4 rows and columns will go into first 4 rows and columns of the global mass matrix. So you just write here. So first row one of the first row of first element. So 156, 22L, 54, and minus 13L. The other two terms will be actually 0. And then second is 22L, 4L square. So this is the same standard procedure, minus 3L square 0, 0. And then you will have here 54, 13L, then you will have 156, minus 22L, and then you will have the fourth row of the first element, minus 13L, minus 3L square, minus 22L, 4L square. So this is the contribution of the first element. Now the contribution of second element. So second element is defined between global nodes 2 and 3. So the degrees of freedom are going to be V2 theta to V3 theta 3. So the contribution of second element will go to third, fourth, fifth, and sixth rows and columns. So we start from third row and third column. So here we will have plus 156, then you will have plus 22L, and then you have 54 and minus 13L. Then here also we will have plus 22L plus 4L square, 13L, and minus 3L square. And then you are going to have, this is 54, 13L. We are adding the contribution of second element, 156 minus 22L, and then minus 13L minus 3L square minus 22L and 4L square. So now you see that here you have contribution from both the elements. Here you have contribution from both the elements. So these are the contributions from both the elements. So this is the assembled mass matrix. Same thing now you do for the stiffness matrix. So let us say EI is same for both the element, L is same for both the elements. So EI by L cube can be taken as a common term. Then the first element contributions will go to the first 4 rows and columns. So we'll write here 12, 6L, minus 12, 6L, and then last to 0, 0. Then here you have 6L, 4L square, minus 6L, 2L square, 0, 0. And then minus 12, minus 6L, 12, minus 6L. Then the last row of the first element, 6L, 2L square, minus 6L, 4L square. Now the contribution of second element will go to the row number 3, 4, 5, and 6, and column number 3, 4, 5, and 6. So here we will have plus 12, plus 6L, and then minus 12 and 6L. And the second row will go to plus 6L, plus 4L square, minus 6L, and 2L square. Then here minus 12, minus 6L, 12, and minus 6L. Then this is 6L, 2L square, minus 6L, and 4L square. So this is again you see these terms have contribution from both the elements. Contribution from both the elements. So yeah, this is the assembled stiffness matrix, mass matrix, and then you have right hand side. So let us look at that also. So is equal to assembled load vectors from the first element. First element contributions will go to the first rows. So we will have QL by 2, QL square by 12, QL by 2, and minus QL square by 12. This is from the first element. Then the second element contributions will go to third, fourth, fifth, and sixth rows. So we'll start from here. QL by 2 plus QL square by 12. Again QL by 12, and then minus QL square by 12. So this is the assembled load vector. And then if you look at the internal load vector, so here from the first element V11 minus M11, and then you will have V21 and M21. Superscript is the element number, subscript is the local node number. Now from the second element you will get V12 minus M12, and then V22 and M22. So this is what you get as the assembled system equation. This is it is irrespective of any kind of boundary conditions. Now let's look at the boundary conditions. So let us say if it is fixed, now the beam is fixed on both sides. So if the beam is fixed on both sides, then V1, the boundary conditions, if you look at V1 would be 0 at all time instances, theta 1 would be 0 at all time instances, V3 will be 0 at all time instances, and theta 3 would be 0. So also V1 double dot, theta 1 double dot, V3 double dot, and theta 3 double dots, they will be equal to 0. And if you look at this term, this will be 0. Now what you have here, this will be 0, this will be 0, and of course these would be non-zero because V1 is 0, so this will be non-zero, this will be non-zero, this will be non-zero, this will be non-zero, but this will be 0 and this will be 0. So finally, from this one, after imposition of boundary condition, so the boundary condition I just stated, after imposition of boundary conditions, we will get the system equation in this form, which would be rho AL upon 420. So because only V2 and theta 2 are unknown displacements as a function of time, so we take the third and fourth equation, and after the solution of course third and fourth equation, we will solve first, second, fifth and sixth equations for V11, M11, V22 and M22. So this equation would be 312. Here it is 0, 0, and 8L square into, we'll have V2 double dot into theta 2 double dot. So these are the third and fourth equations, plus EI by L cube, and then you have 24,008 L square into V2 theta 2 is equal to, right hand side you will just get QL and 0. So this is the system equation of motion for the system, which can again be written in the same form, that M into D double dot plus K into D is equal to F. So this is M, this is D double dot, this is K, and this is your D, and this is your F. So yeah, this is what you get as the equation of motion. So like that we can derive these. So I think I want to stop here, and I will continue a few more elements. I will subsequently I will just discuss how to get the mass matrix for other elements, but this is how the entire assembly, the imposition of boundary condition, and final equation of motion. So this is the final equation of motion you get. Yeah, so I want to stop here, and if you have any doubts and questions, you can ask.
Sir, what were the boundary conditions?
Boundary condition for this problem?
Yes, sir.
Okay, so then let me write the boundary condition. So if you look at the boundary conditions, so first node is fixed. So the displacement is 0 over there and the rotation is 0. So V1t is equal to 0. So also V1 dot at any time instant would be 0. V1 double dot at t will be equal to 0. So that is one. Second is first node is no rotation is also not allowed. So theta 1 t equal to 0. So therefore theta 1 dot at t is 0. Theta 1 double dot at t equal to 0. So these are the boundary conditions at first node. Then if you look at the third global node, so V3 at all time instances is 0. So therefore V3 dot at t will be 0, and V3 double dot at any time instant would be 0. Third node is also not allowed to rotate. So theta 3 at t is 0, and therefore theta 3 dot at t 0, theta 3 double dot at t equal to 0. So this, now if you look at the center node, So the center node, the node number 2, if you draw the free body diagram, so this is node number 2, and in the in the element, see, the forces are like this. So here you will have basically for the second element, so V12, and this will be M12, and this is coming from the second node, so you will have, no, that's the other way around, yeah. No, this is the other way around. So this will be in the node. I know it will be up in the node. It is going to be opposite of element. So this will be V, 1 2, and of course M12 of course will be the same. So that is going to be M12. From this side you are going to have V21 and M21. And so this is the the free body diagram of second node. So you will have this V21 minus V12 equal to 0. So V21 minus V12 equal to 0, that is 1. And the sixth condition is also that M21 minus M12 equal to 0. So these are all boundary conditions. So you basically take only the third and fourth equation, because V1 theta 1 are corresponding to first node and V3 theta 3 are corresponding to third node. They are known. So you take only the second and third equation. In second and third equation, you put V1 double dot 0, theta 1 double dot 0, V3 double dot 0, theta 3 double dot equal to 0. So after you put that, you get this as the equation of motion what I have written. So these are the boundary conditions. Yes.
Sir, suppose if the problem statement had a point moment, like moment at a point and force at a point, but that point did not coincide with our nodes we have taken.
Yeah.
So in that case, like, will we distribute the total rod according to the point where it has been applied?
You can. One is that you discretize the the rod into elements such a way that you have node at that point. So that is one way. The other is you can write the virtual work of that force, and consistent with the shape functions you can calculate the contribution of that load at the two adjacent nodes at the the node within. So that's what you are saying. Let us say, for example, this is the element. So we have local nodes 1 and 2, and but there is a say some force P over here, and there is a moment M over here. So if this is the case, then you write the when you write the virtual work, so you will have the without any integration, you will have you can write, let us say, V transpose at this point, and let us say the coordinate is x0. So V x naught transpose into, you will have P, and minus, similarly you will have theta transpose at x naught into M. So this will be the additional contribution. So rather in the virtual work you will have delta here, delta theta over here, and then this delta V at x naught you will calculate from the shape functions. So h1, h2, h3, h4 evaluated at x naught, and into, of course, you will have the DE. So from this you will finally get this as a 4x1 vector, where h1 is evaluated at x naught, h2 is evaluated at x naught, h3 is evaluated at x naught, and h4 is evaluated at x naught. So you will get this as a again a basically load vector corresponding to this. And similarly, delta theta at x naught, you will write it as dh1 by dx, dh2 by dx, dh3 by dx, and dh4 by dx evaluated at x naught into d. So from that also you will get a vector, a load vector. So it would be basically that load would be distributed to node 1 and 2. So that's one way. This will not be very accurate. So better is to discretize the rod in such a way that you have a node at a point where there are concentrated forces and moments. But nonetheless, you can also do like this.
Okay, sir.
Yeah.
Thank you, sir.
Yeah. Okay. Thank you. So are there any other questions? Anybody?
Hello, sir.
Yeah.
Sir, in boundary condition, the fifth and sixth point which you write.
Pardon?
Like in the boundary condition, the list you just made.
Yeah.
The fifth and sixth point you wrote. Like, why do we consider it in boundary conditions?
It's not really the boundary condition, but now because we are using this condition to substitute in the equation of motion, so I have just put it in another boundary condition. But really the boundary conditions are these, as you rightly said. The first four are the boundary condition, and this is the condition on internal load, the relationship between the internal loads at that node point. So these are not really the boundary condition, but in a way we are saying that the external force and moment at that node is zero. So that is why I have put under the boundary conditions.
Okay, sir. Sir, and the global mass and stiffness metrics are the ones before imposing the boundary conditions, right?
We actually, ultimately we do not use, these. You can say this also as a global mass matrix, this as a global stiffness matrix. But ultimately, what we use for solving these equations of motion is finally this. So usually we refer to this M as the global mass matrix, this K as the global stiffness matrix after imposition of the boundary condition.
Okay, sir.
Yeah.
But in statics it is opposite, right? That there it is before imposing.
No, actually everywhere it is same.
Okay.
Yeah. Yeah. Are there any other questions, doubts? Hello, anybody? Yes.
Do we have a class this Saturday?
Yeah, I have scheduled a class on Saturday because there were too many holidays coming. So last week we had Friday the MTech project presentation, so I did not take a class. So that is why I have also scheduled class on Saturday, that is 16th.
Okay.
So the next, of course, next class is going to be on Thursday, 14th, and then we will have class on 16th.
Okay.
Yeah. Okay. So any other question?
Sir, I have one doubt regarding the homework you had given in the previous class.
Yeah.
So like, since it was a one-dimensional problem, sir, right?
Yeah.
So we do not need to consider that body force term in the elemental level equation.
You will have, let us say, you will have force per unit length along the x direction. No? So that you have to consider.
Okay, means as a traction, we will have to consider that term.
Yeah, you can say that traction, in place of traction, you will have forces at the two nodes, end nodes, and in place of body force, you will have force per unit length along x direction.
Okay.
Yeah.
Okay. Thank you.
Yeah. Any other question? Anybody? Okay. So if there are no questions and doubts, I'm stopping. Thank you all for your attention.